Good day, everyone. This is the Module 2 of Advanced Mathematics for Industrial Engineering. This module is about the determinants. The duration of this module is 9 hours. So for the introduction, the determinant is useful for solving linear equations. In what way? By capturing how linear transformation change area or volume and changing variables in integrals. Because as we recall, in integrals, we are assigning numbers to functions to describe such changes. So, determinants can be viewed as a function whose input is a square matrix and whose output is a number. Later on, you will know why it has an input of a square matrix and has an output of a number. And now for the objectives. At the end of the chapter, students are expected to learn the following. Number 1. The definition and properties of determinants. Number 2. Methods of finding determinants. Number 3. Cofactor expression and inverses. But before we go to the pretest, I want you to watch a video to further explain to you and give you an idea what is the application of a determinant.
Let's go back to the basics. Determinants. Let's take a matrix of 1, 2, 0, 2, 1, 0, 0, 0, negative 3, and let's use this matrix to transform every vertex on a unit cube of length, width, and height 1, aligned along the x, y, and z axes. After transformation, you'll see that we have a completely different object than we had before. But now I have a bit of a question. How much larger is this new transformed object? We could solve this problem with numerical integration by encapsulating both objects in a larger cube and performing Monte Carlo integration. After integration, we can say that the larger object is about 9 times bigger than the unit cube. Now, let's think of this problem a little differently. During matrix transformation, most vectors will stretch and rotate. However, there are certain vectors that only stretch and do not at all change direction. These vectors are known as eigenvectors, and the amounts by which they stretch are known as eigenvalues. If we align the sides of our unit cube along these eigenvectors and perform a matrix transformation on each vertex in the cube, we'll find a rectangular prism that has not been skewed at all. This makes finding the ratio between the new transformed object and the original unit cube kind of trivial. It's simply the length times width times height of the new cuboid. Now, because we align the unit cube along eigenvectors, and each side of the unit cube is of length 1, after transformation, the new length, width, and height are all eigenvalues. So how much bigger is the object after transformation? Well, it's simply a product of all of the eigenvalues, which, in this case, is exactly 9. Here, I suppose it makes sense that any object's volume will increase by the amount of stretching in each dimension, which is exactly what we said before. The new volume is a product of the eigenvalues. Now, at this point, you might be thinking that we're pretty clever, but mathematicians have at least one more trick up their sleeve. Determinants. So let's do it. Let's find the determinant of our transformation matrix. It will be 1 times negative 3 minus 0 times 0, subtracting 2 times negative 3 minus 0 times 0, plus 0 times 2 times 0 minus 1 times 0, which is equal to negative 3 plus 12, or exactly 9. The same as we saw before. And that's that. A simple determinant can be determined by comparing the new to the old.
I hope that video gave you a good explanation about what is a determinant as well as its application. Now let's proceed to the pretest. You will answer this on a separate paper or you can use Microsoft Word.
and attach your answer file to the post in our Google Classroom. So this test is just to use to test your prior knowledge about the topic. So this is about equivalence relation. By definition, an equivalence relation on a set is a relation satisfying three conditions, named as the first is reflexivity. This is about each element A of the set is equivalent to itself. Next, symmetry means if A is equivalent to B, then B is equivalent to A. And lastly is transitivity. It means that if A is equivalent to B and B is equivalent to C, then A is equivalent to C. So, you will show that row equivalence of matrices satisfies these three conditions. So this is a hint for you. Show that for each of the three elementary row operations, these conditions hold. You can start answering now. So after you answer the pretest, let's go now to the lesson proper, or the course methodology. The determinant of a matrix product AB or BA can be written as the product of the determinants of the factors. It is interesting that determinant AB is equal to determinant BA. Although we already know that matrix AB is not equal to matrix BA in general. In linear algebra, the determinant is a scalar value that can be computed from the elements of a square matrix and encodes certain properties of the linear transformation described by the matrix. So, as we recall, a scalar value is a physical quantity that is described by its magnitude. Examples are volume, mass, time, and etc. So, in getting the determinant, a square matrix is involved. So the determinant of a matrix A is denoted as that quantity A, or just that space A, or the absolute value of A. So geometrically, it can be viewed as the volume scaling factor of the linear transformation described by the matrix, because as you watched the video earlier, determinants is used in computing the transformation of an object, a 3D object, which has a volume. So it includes volume scaling. This is also signed volume of the n-dimensional parallelepiped spanned by the volume of row vectors of the matrix. So, what is a parallelepiped? A parallelepiped is a three-dimensional object which is composed of 6 parallelograms sides. Okay, so this has similar descriptions in the video that you watched before, because the transformation is made by the spanning of the column or row vectors of a matrix. So the determinant is positive or negative according to whether the linear transformation preserves or reverses the orientation of a real vector space. So the determinant can be positive or negative based on the transformation or the linear transformation. Okay? So in the case of a 2 by 2 matrix, meaning 2 rows and 2 columns matrix, the determinant may be defined as, so you can use this formula. The determinant of matrix A is equal to the matrix A, B, C, D is equal to D minus B times C. Okay, so this formula can be used in case of a 2 by 2 matrix. Because, as you know, a 2 by 2 matrix is a square matrix. Similarly, for another square matrix, which is a 3 by 3 matrix, meaning 3 rows and 3 columns matrix. Matrix A, its determinant is, the determinant of matrix A is equal to, the matrix itself is equal to, we will get the product of the first element, the element in the upper left corner, which is A, and the elements of E, F, H, I. So, how do we get this element E, F, H, I? We get this by getting all the elements that do not lie along with the column of element A, as well as with the row of element A. So these elements do not belong to the column and the row which element A belongs, minus element B. So element B is in the middle, the upper part middle, first row, multiply by the element D, F, G, I. So how do we get this element D, F, G, I? We get that by getting all the elements that do not lie on the rows and columns which element B belongs. Next, plus the element C multiplied by the elements D, E, G, H. So how do we get elements D, E, G, F? So it is the same with the previous ones. We just get all the elements that do not lie along with the row and column which element C belongs. So we can also write this formula like this, the following formula, equals A, E, I. So we just multiplied the outside element, which is A, to the diagonal elements from upper left to the lower right, which is EI. Okay, so plus BFG. So here you notice that if the sign or the operation of an element is minus or negative, you will start multiplying from the upper right to the lower left, which is FG. Okay, next is plus CDH. So this is the same with the first multiplication, minus CEG. So we will just subtract the product of the element C and the diagonal elements that we do not use before in this addition. Okay, minus BDI. So it is the same. We subtract the product of the element B and the diagonal elements DI, which we do not use before in the addition part. Okay, and same for the last one, which is minus AFH. Okay, you can use that formula, or you can just simply use a shortcut, which is illustrated in the next. So the determinants of a 3 by 3 matrix given matrix A with its elements. So as you notice, the first column is written here, as well as the second column. So what is the purpose of them? So their purpose is for the shortcut computation. You notice that this operation is just representation of the or the application of the formula that we discussed here. Okay, but in this next computation, this is the computation we got from using the shortcut, so that you will not have to use this long formula. Okay, so after you write the first and the second column here, you will get the product of all the diagonal elements from the upper left corner to the lower right corner. For example, the first one is 3 multiplied by negative 4 is equal to negative 12. So negative 12 multiply by 4 is negative 48. So that is why it is written here as negative 48. Okay, so next, 9 multiplied by positive 7 is equal to 63. Multiplied by positive 5 is equal to 315. That is why it is written 315 here. Next, negative 2 multiplied by positive 2 is equal to negative 4. So negative 4 multiplied by positive 6 is equal to negative 24. That is why it is written negative 24 here. Okay? So next, we will just subtract these products. So how do we get these products? We will now proceed from the lower left part up to the upper right part of the diagonal elements. So let's begin here. 5 multiplied by negative 4 is equal to negative 20. Multiplied by negative 2 is equal to positive 40. That is why it is positive 40 here. Okay? So next is 6 multiplied by 7 is equal to 42. Multiplied by 3 is equal to 126. Next, 4 multiplied by 2 is 8. Multiplied by 9 is 72. Okay, that's why you have your computation here of determinant. So, just combining them, we got the determinant of A is equal to 5. So now we know that determinant uses a square matrix, okay, that has an output of a number. So we got 5 as the output of our determinant A. Okay? For the second example, it is also a 3 by 3 matrix. Given matrix A with its elements, so first we have rewritten the first and the second columns to do our shortcut computation. So 11 times 20 times 15 is equal to 3,300. Negative 2 times negative 5 times 13 is equal to 130. 16 times 9 times 7 is equal to 1008. So minus 13 times 20 times 16 is equal to 4160. Plus 7 times negative 5 times 11 is equal to negative 385. Plus 15 times 9 times negative 2 is equal to negative 270. So we just simplify them and get this number. The determinant of matrix A is equal to 933.
Now let's go to the minors and cofactors. So here we have a given matrix. So consider these elements of a matrix. Okay? So this letter M, M sub 1, 1, M sub 2, 2, 2, M sub 3, 3, these are called the minors. Okay? While the C sub 1, 1, C sub 1, 2, 2, C sub 3, 3, these are called the cofactors. Okay? So how do we get these minors and cofactors? First, for the minors, for the first one is m sub 1, 1. So to get the minor or m sub 1, 1, we just select the element that lies on the m sub 1, 1. So what is the element that lies in m sub 1, 1? So it is this, the number 5. It is the element that lies in the upper left corner of the matrix because it is a sub m sub 1, 1. Okay, so we will get all the elements that do not belong to the row and column that the element m sub 1, 1 belongs. Okay, so cross out the first row and the first column. So what left is 5, 6, 4, 7. Now, we will just do this process. So, we will get the product of the diagonal elements, which is 5 and 7. 5 times 7 minus the product of the second diagonal element, which is 4 and 6. Okay, that's why we got 11. So the minor of the first element of the matrix is 11. Okay, now how to get the cofactor? Cofactor of the first element or the C sub 1, 1. Okay, so here we have a constant which is negative 1. So this is always negative 1. It is a constant. So how do we get the exponent? So we get the exponent by adding the position that is written on the subscript, which is 1, 1. So 1 plus 1 is equal to 2. Okay? That's how you get the exponent. Then multiply by the minor. The minor of the element in C sub 1, 1. Okay? So 11 is the minor. That's why it is indicated in C sub 1, 1. So just substitute the value you get from the minor to this part of the cofactor. Okay? So u squared negative 1, then multiply by 11, so you get positive 11. Okay? So you now get the minor and the cofactor of the first element of this given matrix. Okay? So the same with the other elements. For example, we want to get the minor and cofactor of the element in the second row and that belongs to the third column. Okay, so what is that element? So second row and third column. So it is 6. Okay, so what is the position of this element? It is M sub 2, 3 or C sub 2, 3. Okay, because it belongs to the second two rows and 3 the third column. Okay, so to get the minor of that, we will just get all the elements that do not belong to the row and column that that element belongs. Okay, so we will cancel this column and we will cancel this column. So what's left is 5, 4, and 3, 4. Okay, so first we will multiply the diagonal elements, which is 5 and 4. That's why here it is 5 times 4 minus the another diagonal elements, which are 3 and 4. So 3 times 4, 4, okay? So simplify, it is 8. So the minor of that element is 8. Now, we will compute its cofactor, okay? So again, the constant, negative 1. Then, how do we get 5? We get 5 by just adding the two number subscript, okay? Which is 2 and 3. So 2 plus 3 is 5, okay? Then we will just substitute the value we get from the minor, which is 8. Then we just simplify, it is equals to negative 8. Okay, so now you know how to get the minors and cofactors of a given matrix. So now, what is the purpose of cofactors? So the purpose of cofactors is to get the determinant of that matrix. Okay? For this computation, for the first row. Okay? So to get the determinant of that matrix, the example above, okay, which is this, so we will get its determinant since we got its cofactors. So first, we will just multiply the first element to its cofactor. Then we will just multiply the second element of the row to its cofactor, as well as with the third element. Then we will just add them all. And now we got the 146 as the determinant of matrix A with reference to the first row. Now, what if we consider the second row as the reference? So, the element in A sub 21 is -4. Then we will multiply it by its cofactor. The same with the element in A sub 22, which is 5, multiplied to its cofactor. And the same with A sub 23 element. Now, you notice that the value that we got from the first row, reference, is just the same in the second row. Okay? So, if you try to make reference to every row, the answer is the same. So, the value of the determinant is the same. Okay? So, for the third row, it is the same. And also, if you make the reference of columns, just like here, the first column, the answer is also the same. The second column, so the answer is the same. And the third, the same. Okay, so that's the application of getting the cofactor. So it is used in finding the determinant. Now let's go to the expansions of a third order determinant. Okay, so here, number 4, we have an example of a matrix. Matrix D is equal to
its elements. So it's also a square matrix, a 3 by 3 matrix. Okay? Now for the expansion of first row, you notice that this equation follows the given equation above. So let's go back to that equation.
So this is the equation that is used
In the third order determinant. So we will use this equation for it.
first. You will just put the
First element with the elements that do not belong to the row and the column that the first element belongs. So these elements are 10, 9, 5, 7. Okay? Minus the second element of the first row. Multiply by the elements that do not belong to the row and column of the second element of the first row, which are 7, 9, -6, and 7. Then last is plus the element of the first row, the third element of the first row, which is 5. Multiply by all the elements that do not belong to its row and column, which is 7, 10, -6, and 5. Okay? So it is equal to 6 multiplied by the difference of the product of the diagonal elements. Okay? So 10 times 7 is 70 minus 5 times 9 is 45 minus 8. So 7 times 7 is equal to 49 minus -6 times 9 is 54. -54. So double negative will be positive. That's why it is positive 54 here. Next, plus 5. 7 times 5 is 35. -6 times 10 is -60. So double negative sign again, it will be positive here. So plus 60. So now we get the expansion of the first row. D is equal to -199. So it is called as the third order or the expansion of the third order determinant. So next, for the second row and the expansion of third row, it will be the same, okay? Whether what you use as your reference, okay? So the result will be the same for the expansion of a third order determinant when you use this formula. Even if you use the expansion of the columns, the first and second, it will produce the same. As you notice, they are all negative 199. Okay? Now let's go to the determinant of a triangular matrix. So when you say a triangular matrix, all the elements with the value of positive or negative other than 0 forms a triangular shape. Okay? So 18, 19, 20, 21, negative 16, 17, 20. So they form a right triangle matrix. That's why it is called a triangular matrix. Okay? So in this case of a triangular matrix, you will just multiply the first element in the first row in the first column, which is negative 18, with the diagonal elements that do not with the diagonal element that do not belong to its row and column. So we will just multiply it with one diagonal element from the upper left corner to the lower right corner, which is 19 and 20. So negative 18 times 19 times 20 is equal to negative 6,840. So that is the determinant of matrix A for a triangular matrix. Okay, so you remember that formula or the format of solving for a triangular matrix.
So now for the properties of determinants. The first property is determinant A is equal to determinant A transpose. So this means that the determinant does not change if we interchange columns with rows. Okay? Because when we say A transpose, we are going to interchange the rows and columns of the original matrix A. So their determinant will be equal. Okay, so next property is this. So this means that the determinant changes sign if we interchange two columns or two rows. Okay, because in this example, the first row is interchanged with the second row. Okay, so when we do that, the determinant will change its sign. So from positive to negative. Next property is this. If two rows or two columns are the same, then the determinant is 0. Because here in our example, you notice that the first row and the second row are the same or equal. So the determinant will be 0. And in the second matrix, you notice that the first column and the second column are equal. That's why their determinant is equal to 0. Next property is if we multiply the elements of one row or one column with the same number, then the determinant is multiplied with this number. So in the example, each element in the first row is multiplied by this Greek letter symbol lambda. Okay, so suppose this Greek letter symbol is a number. Okay, if you multiply the same number to the row or to the next matrix, which is the first column, then the determinant should be multiplied with the same number. That's why you see here that the Greek symbol lambda is to be multiplied with the determinants. Next property is this. If the elements of a row or a column are multiples of the elements of another row or column, then the determinant is 0. So here in the example, you notice that the first row, okay, so they are multiplied by the symbol lambda, okay, but their elements, okay, their elements which are a sub 1, a sub 2, a sub 3 are multiples of the elements in the second row, okay. So when this happens, their determinant is equal to 0. Next, here is the first column is multiplied again by the Greek letter lambda. And you notice that the elements in the first column, A sub 1, B sub 1, C sub 1, are multiples. Okay, multiples of the elements in the second column. And when that happens, their determinant will be equal to 0. Next property is if any element of a row or column is the sum of two numbers, then the determinant could be considered as the sum of other two determinants as follows. Okay, here in the example, the elements in the second row is composed of sum of two numbers. Okay, so b sub 1 plus d sub 1, b sub 2 plus d sub 2, b sub 3 plus d sub 3. So if this happens, okay, any of the row, any of the row or any of the column, if this happens, then the determinant is also the sum of other two, okay, will be equal to the sum of the other two determinants. That's why you notice here it is equal to the sum of this matrix, okay, and this matrix. So when this happens, the determinant will be the sum of two determinants, okay. So next property is this. If we add the elements of a row or a column to the corresponding elements of another row or column, then multiplied by a number, then the determinant does not change. Okay? So in this example, you notice that the elements of the first row, which are a sub 1, a sub 2, a sub 3, are multiplied by a number. Okay? A number represented by lambda, the Greek letter lambda. Then the product is added to the values or the elements of the second row, which are b sub 1, b sub 2, b sub 3. So if we do that, the determinant does not change because as you notice, it is equal to this determinant of a matrix. Okay, so the determinant will not change. So this property is frequently used when we need to make the elements of a row or column equal to 0, thus bringing the determinant to a form which can be computed easily, like upper triangular. Okay, so we will be using this to make some of the elements equal to 0 when we are computing them, like the upper triangular. When we say upper triangular matrix, it is like this. Okay, so this is an upper triangular matrix wherein the zeros below the matrix form a triangle. Okay, this is called an upper triangular matrix because the upper part of the matrix is composed of elements which are not equal to 0, while the lower part is composed of zeros. Last property is this. So if the determinant A is different than 0, so if the determinant is not equal to 0, then the inverse matrix exists and is given like this. A raised to negative 1, meaning it is an inverse matrix, is equal to 1 over the determinant, which must be not equal to 0 because uh, that is the properties all about. Okay, so this is the format. Positive, negative, positive,
negative, positive, negative, positive, negative, positive. Okay? So now, what is an inverse matrix?
So this is the inverse of a matrix. Okay? So the inverse of a matrix, n by n matrix A, is another n by n matrix denoted by A raised to negative 1. Okay, so we write the inverse of a matrix by raising the matrix to negative 1. Okay, such that A multiplied by the inverse of A is equal to A inverse multiplied by A. Okay, is equal to I. So what is I? I is the n by n identity matrix. So when you see I, it means it is an identity matrix. So we got the identity matrix by multiplying a matrix by its inverse. Okay? Because in this example, we multiply matrix A with its inverse. That's why we get the identity matrix. So not all square matrices have an inverse matrix. So you have to take note of that. Not all square matrices. Okay? So if the determinant of the matrix is 0, then it will not have an inverse, as we mentioned earlier. Okay, so you remember that. And the matrix is said to be singular. So if a matrix has no inverse, then it is said to be singular. Otherwise, it is non-singular if they have inverses. Okay? So next is the formula for finding the inverse. So given any non-singular matrix A, its inverse can be found from the formula A raised to negative 1, so meaning it is the inverse of A, is equal to ADJ A over the determinant of matrix A. So what is ADJ? So it is the adjoint matrix. Okay? And of course, the the absolute value A is the determinant A. So the procedure to get the adjoint matrix is as follows. Okay, we have different stages for that. So for the first stage, we will find the transpose of matrix A, which is denoted by A raised to T. So first step, we will get the transpose. Next, the transpose is found by interchanging the rows and columns. You already know that, okay? So for example, the first column of A is the first row of the transpose matrix. The second column of A is the second row of the transpose matrix, and so on. So it is just getting the transpose by changing the rows to columns. Okay? Next, the minor of any element is found by covering up the elements in its row and column. So, for the second stage, we will find the minor, okay, as we discussed earlier, and finding the determinant of the remaining matrix by replacing each element of the transpose matrix by its minor. So we will replace the each element of our transposed matrix by the minor that we got. Okay? We can write down a matrix of minors of A transpose. Okay? So that is the second stage or the step 2. Next is the step 3. The cofactor of any element is found by taking its minor and imposing a place sign according to the following rule. Okay? So you already know how to get the cofactor, right? So when you get the cofactor, then you will use this sign or this rule. So for the first row, you have first is positive, negative, positive, and so on and so forth. So it is only alternately, okay? Positive, negative, positive. For the second row, it starts with negative, positive, negative, then so on and so forth. You will just alternate it. And for the third row, it is like the first row. Okay, so remember that rule. Now let's go now to the example, okay, to finding the inverse. So find the adjoint or the inverse, okay, of matrix A. So this is the given matrix, okay, so it is a 3 by 3 matrix or a square matrix because they have equal number of elements in the rows and columns. So for the solution, follow the stages we have discussed, okay? So first, find the transpose of the given matrix A by taking the first column of A to be the first row of A transpose and so on, okay? That's why when we get the transpose, you notice that the first row, which is 1, -2, and 0, becomes now the first column, okay? The second row becomes the second column. The third row becomes the third column, okay? So that is the transpose. So after finding the transpose, we will now find the minor of each element, okay, in the transpose matrix. So the minor of the element 1, the first element, in the first row in the first column, okay, is obtained by covering up the elements in its row and column. So we will just cover the the row which it belong, and the column which it belong, it's belong, okay? So the remaining elements is 1, 2, 5, 3. That's why it is 1, 2, 5, 3 here, okay? And finding the determinant of this, which is -7. So you already know how to find the determinant, okay? Because we have discussed it earlier. So how do we get -7 here? Because we multiply 1 times 3, so it is 3. Then we subtract it from the product of 2 and 5, which is 10. So 3 minus 10 is -7, okay? So you should know how to find the determinant because we have discussed it earlier. So the minor of the element 3, okay, so that is the second element in the first row of the transpose, okay, is found by covering up elements in its row and column. So we cover this second column because the element 3 belongs to that, and we cover the first row because the element 3 belongs to that. Okay, so the remaining elements are -2, 2, 0, and 3. So we get a determinant of -6 from that, right? So we continue in this fashion and form a new matrix by replacing every element. So we will going to replace every element here. So 1, 2, 3. So there are 9 elements here. We will do the process 9 times, okay? Replacing each element, okay? Replacing each element with its minor. So the matrix of minors of the transpose is this, okay? So next, then impose the place sign. This result in the matrix of cofactors, that is the adjoint of A. So we will now apply the rule, okay, the rule of the sign. So going back, this is the rule of the sign for the first row, second, and third, okay? It is just an alternating sign, positive, negative, positive for the first row, and negative, positive, negative for the second row, and the third row is just the same with the first, okay? So here you notice that -7 remains -7 because the sign for this part is positive. So it will remain unchanged. But -6 becomes +6 because the sign here is negative. So negative times negative will be positive. Okay? Then -10 is the same because the sign here is positive. So you will just apply the rules, okay, of the sign. So 14 becomes negative, okay? 3, the same. 5 becomes -5. Next, 7, the same. 0, the same. 7, the same. Okay, so we have now our adjoint of matrix A. So next, notice that to complete this last stage, each element in the matrix of minors has been multiplied by 1 or -1 according to its position. Yes, because we have applied the rules of the sign. Okay? So it is straightforward matter to show the determinant of A is 21. So how do we get 21? We get that by the methods of finding determinant. Okay? You will just the you will just use the minors and cofactor methods as that we have discussed earlier. Okay? So once you get the determinant of A, which is 21, finally, you will just multiply all the elements of the adjoint of matrix A with the reciprocal of the determinant, which is 1 over 21. So when you multiply it, that will be the inverse of the given matrix. Okay?
Alright, so now let's go to calculating determinants using row reduction. Okay, so we can also use row reduction to compute large determinants. So the idea is to use elementary row operations to reduce the matrix to an upper or lower triangular matrix, using the fact that the determinant of an upper or lower triangular or diagonal matrix equals to the product of its diagonal entries. So first, what are the triangular matrix, the upper and the lower triangular matrix, as well as the diagonal matrix?
So this is the upper and lower triangular matrices. Okay?
You say that it is upper triangular matrices if all the elements, okay, all of the elements from the diagonal, okay, from the upper left corner to the lower right corner, okay, if all the elements under it is equal to 0. So it is called upper triangular matrix because all the elements under it is equal to 0 while all the elements above it is not equal to 0. Okay? Next, you call it as lower triangular matrix if the elements above the diagonal is equal to 0 and all the elements below the diagonal elements are not equal to 0. So that is the upper triangular matrix and the lower triangular matrix. So now this is an example of diagonal matrix. Okay? So we say that a matrix is a diagonal matrix if all of the elements is equal to 0 except, okay, so except with the diagonal elements, they are not equal to 0. That's why it is called as a diagonal matrix. Okay? So now you know about the lower and upper the triangular or diagonal matrix. It is stated here that their determinant, okay, their determinant is equal, okay, equal to the product of its diagonal entries, okay, or diagonal elements. Okay, so here we will first reduce a matrix to an upper or lower or diagonal matrix. Okay, then we will just get the product of the diagonal entries to get the determinant. So these properties we have discussed earlier. Okay, let's go now to the example. Okay, so use row reduction to compute the determinant of this given matrix. Okay, so this matrix is a 4 by 4 matrix. Okay, so this is also a square matrix. So for the solution, we first interchange the second row and the third row. Okay, and when we do that, we will change the sign of the determinant. That's why we have a negative sign outside here, okay? Why do we do that? Because it is according to this property, okay? When we interchange a row to a row, okay, or a column to a column, then the determinant will change its sign, okay? If it is positive, then it will be negative. Now, so now we will just subtract the elements of uh, the first row to the elements of the second row, okay, to get the second row. So here, 2 becomes 0 because we subtract 2, the element of the first row, to the element of the second row, which is 2. Okay, so 2 minus 2 is equal to 0. That's why it is 0 here. Okay, so next, negative 1 minus 3 is equal to negative 4. That's why it is negative 4 here. Next, so it is the same computation, okay, for the rest of the elements in the row 2. That's why it is indicated that the row 2 is changed here. Okay, so by doing that row operation, the determinant does not change, okay, because it is also indicated in the properties. Okay, so by doing that row operation, the determinant is not changed. Okay, so you can check that. So next step is we now add, okay, we now add the elements of row 4 and row 3, okay, to yield the new row 4, okay. So from this previous matrix, we just add row 4 and row 3. So 0 plus 0 is equal to 0. That is why it is 0 here in row 4. Next, 4 plus negative 4 is equal to 0. That is why it is 0 here in row 4. Okay? So next, 3 plus negative 3 is equal to 0. That is why it is 0 here in row 4. Next, negative 3 plus 2 is equal to negative 1. That's why it is negative 1 here in row 4. Then again, the determinant does not change because it is stated in the properties of determinants. So next, we will just add the elements of row 3 and row 2 to get the new row 3. Okay, so from this previous matrix, we just add them. So the element of row 3 is
0. Okay, so we add 0 plus 0 is equal to 0. That's why the first element in the row 3 is 0. Next is 4 plus negative 4 is 0. That's why the the second element in the row 3 is 0. Okay, so next, negative 4 plus positive 3 is equal to negative 1. That's why it is negative 1 here. Okay, so next, negative 4 plus negative 3 is equal to negative 7. That's why it is negative 7 here. Okay, so again, the determinant does not change because it is according to the properties of determinant. And now we get an upper triangular matrix. So we call this an upper triangular matrix, okay? Because all the elements above the diagonal, okay, are equal to the diagonal itself is not equal to 0. Okay, so this is a triangular matrix. Now we can compute for the determinant of the upper triangular matrix. Okay, so we just change the sign of the first element because we have negative here, the outside. Okay, so it will be negative 2. So we will ignore, okay, ignore the column. Okay, so we ignore the column that 2 belongs, okay, and the row that where it belongs. So the remaining elements is this. Okay, so here we will just get the product of the first element and the product of the diagonal. So the diagonal is negative 4, okay? Next negative 1 and last is negative 1, okay? We will just multiply them all and we got 8. Okay? So this is now the determinant of the upper triangular matrix. So for the post test, okay, so number 1 is about the general properties of determinants. You will illustrate each statement in theorems 1 and 2 with an example of your choice. So what are those? These two, okay? you will make an example that proves this. Okay, determinant A is equal to the determinant of A transpose. Then the second one is this. Okay, you will prove this, that when you interchange two columns or two rows, so the determinant should change. Okay, so these are the two. So you will just give an example for that too. Okay. Next is the second order determinant. So expand a general second order determinant in four possible ways and show that the results agree. So when you say second order determinant, it is a 2 by 2 matrix. Okay. So you will just expand, okay, a 2 by 2 determinant. Okay. So just like this, the previous example. Okay. So the expansion of each row. Okay. So this example is a 3 by 3, okay? But in the instruction, you're going to make a 2 by 2 only, okay? Because in this example, it is an expansion of a third order determinant because it is 3 by 3. So you will just use this formula for 2 by 2 by 2, okay? Next, number 3, third order determinant. Do the task indicated in theorem 2. So what is the theorem 2? This one, okay? Uh, when you change two columns or two rows, you will uh, change the sign of the determinant, okay? So this is the one that you will do for that item, okay? Calculating the determinants using row reduction. So that is for third order determinant, okay? So you will make your own, okay? You will make your own matrix, okay? Of a third order determinant, meaning a 3 by 3 matrix. So it is the same with the number 2. You will make your own 2 by 2 matrix. Okay? But here in number 3, you will also evaluate the D or the determinant by reduction to triangular form. So you will apply this. Okay? You will reduce the the matrix that you have chosen to a triangular form, and you will apply this formula. Then for the number 4, the expansion of numerically impractical. Show that the computation of an nth order determinant by expansion involves n, n factorial. So it is n factorial multiplications, which if a multiplication takes 10 raised to 9 seconds would take these times. Okay? So here you will just show that this uh, number of multiplications 10, 20, 10, 15, 20, 25. Okay, you will just show that when each multiplication, okay, when each multiplication takes 10 raised to negative 9, it will result to these values: 0.004 seconds, 22 minutes, for 15, and for 20, 77 years, for 25, 0.5 times 10 raised to 9 years. Okay, so you will just show that that the computation of an nth order determinant by expansion involves n factorial. Okay. Next is number 5, multiplication by scalar. Okay, so here when you say scalar, it is a constant value. Okay, constant value that describes the magnitude of a quantity like volume, mass, okay? So temperature. So you will use any, okay, any value. You will give an example. You will multiply any constant to an example of a matrix that you will be choosing, okay? To show that determinant k is the scalar value multiplied by the matrix A is equal to k, the scalar value raised to n, okay, multiplied by the determinant. So it is not the same with k determinant A, okay, because it has exponent of n. So you will show that in your example. Next, number 6, minors, cofactors. So you will just complete the list in example 1. So this is the example 1, okay? So you will just complete the list for it. You will find the minors and cofactors of this example number 1. By doing that, you will be doing like this, okay? You will get all of this, the minors and all the cofactors of the first example, okay? And for the last part, you will evaluate determinants, okay? From 7 to 14, you will get the determinants. So depending on what method you will use, okay?